Okay, so last week we concluded electrostatics. So if you have any questions about electrostatics, we can review them now.
In the question that we solved last week, I did not understand what Q prime and Q double prime.
What was the problem? Of a infinite plane dielectric, two dielectrics. So I think it was this one.
Yes, it was an infinite plane with a point.
So this was the problem that we were studying. But if we would review what we did in a conductor, this is a conductor. This is vacuum. And then we had this charge over here, Q. Well, since it was a conductor, we already knew that the electric field in the conductor is 0. So we didn't need to worry about the electric field in that region. On the other region, in the vacuum, we said that the conductor, the charge that we put there will induce some surface charges on that interface, and those surface charges will act as if there is another point charge on the other side. So this, and it would be, the charge will be minus Q. So this is D, this is also D. So let's say this is at the position R0, this is at the position R0 prime. So the potential R, if R is in the vacuum, was given by 1 over 4 pi epsilon 0, Q over R minus R0, the potential created by the actual charge, plus the potential created by the charges on the conductor. And they behaved as if they are just a point charge at R0 prime. So this second term over here is basically due to all the charges over here. Now let's come to the case of the dielectric. Well, the dielectric is not a conductor. So there might be electric field, non-zero electric fields in it. But still, depending on the dielectric constant or the permittivities of these two medium, there will be some surface charge induced on this surface. And the claim was that this surface charge also behaves as if there is another charge on the other side. So for, let's say, and we said that let's take its image here. This is D, this is also D. But this time it is not equal to minus Q. We called it Q prime. Initially we didn't know what that charge is, so we just called it Q prime. So if the radius is in dielectric 2, in region 2, let's say, this is region 1, this is region 2. For a point in region 2, these bound charges on the dielectric just behave as if there is another charge on the other side. The difference from the dielectric is that this time, that point charge, which is on the other side, that the image charge, is not equal to minus Q. And V R is equal to 1 over 4 pi epsilon 0, Q over, again, let's say this is at the point R0, this is at the point R0 prime, 4 pi, now divided by R minus R0, plus 1 over 4 pi epsilon 0, Q over R minus R0 prime. This is for a point on this side. The potential can be written in this form. Of course, this potential is created by the bound charges plus this charge, not two charges. But the bound charges over here, they just behave as if there is another point charge on the other side. And let me also add the dielectric constants. So this is epsilon 2 permittivity, this is epsilon 2. Now, if R is in region 1, that is for a point over here, it will see that charge over there at the same position, but the charge will be different. Now, it won't see the total charge Q, it will see some other charge. So V of R will be equal to 1 over 4 pi epsilon 1 Q double prime over R minus R0. Then, of course, there was the question of what is Q double prime, what is Q prime, and if I'm not wrong, Q prime was equal to epsilon 2 minus epsilon 1 divided by epsilon 2 plus epsilon 1 Q, and Q double prime is equal to twice epsilon 1 divided by epsilon 1 plus epsilon 2 times Q. This was what we had obtained, if I'm not wrong. Now, how did we obtain those? Well, we know the properties of the potential. V is continuous on the boundary. Which is, in fact, the same thing as saying that E parallel is continuous on the boundary. And D perp is continuous on the boundary. Since there are no free charges. If there are some free charges, the component of D perpendicular to the surface need not be continuous. But since there are no free charges in this problem, it is continuous. So these two conditions allow us to determine what Q prime and Q double prime are. And since we are satisfying all our boundary conditions, the potential we obtain satisfies our boundary conditions, satisfies the corresponding Poisson equation. So it is unique, so we are done. We guess the solution, it works. Not all the time your guess works. For example, if you try to do it similarly for a conducting sphere or a dielectric sphere in a dielectric, well, we already know the solution in the case of a conducting sphere in vacuum. So if you just assume that the image method will work similarly, it does not.
In region 1, why didn't we consider only Q, charge Q? Because Q is in region 1.
Now Q is in region 2. Q is in region 2, but remember, there are all these bound charges over here which will contribute to our potential. So in region 1, there is the Q plus the bound charges on this interface. And the claim is that the bound charges on this interface, they just behave as if there is discharge on the other side.
Hocam ta başlarda biz hani rho diye bir şey tanımlıyorduk ya charge. Ben işte onu tanımlayamıyorum.
Give me an example where you, by the way, do you have a question on this one? No, okay. So do you have an example where you cannot define it?
İşte hocam böyle bir küre olsun. R'ye çarpıyor. Artı Q yüklü olsun. Rho nedir?
Is this a conducting cube? Conducting sphere? What do you know about the charge in this problem? It should be uniformly distributed over the surface. So inside it is 0. Outside, are there any charge outside my sphere? No, so outside rho is also 0, only on the surface. What is the volume of the points for which r is equal to the radius? Zero. So what should be the charge density on the surface? You see, if I take some volume over there with area A, let's say dA, height, let's call it dH, the volume is just dA times dH. And the charge density, let's say it has a charge dq, rho at that point is dq over dH times dA in the limit as dH and dA, they both go to 0. Let me take that limit in this order. So as I change dH, does the charge in my volume change? I keep dA fixed. I'm just considering this limit first, this dH limit. I keep dA fixed and take the limit dH goes to 0. So does dq go to 0? It doesn't go to 0. So dq doesn't go to 0, but dH goes to 0. So this is infinite already. Well, if I take dA to 0, infinite over 0 is even more infinite. So this diverges. So basically rho goes to infinity on the surface. So this is my function that is 0 almost everywhere. It diverges on the surface, and it should be independent of theta and phi. Well, I already have a candidate for this. This is equal to Dirac delta r minus r. And let's say I will multiply it by, in general, some function of theta and phi. But I know that the charge density doesn't depend on theta and phi. Since charge density doesn't depend on theta and phi, we said that the charge is distributed uniformly over the surface. That basically means independent of theta and phi. F should be independent of theta. F should be a constant. So let's just call that constant A. So this is my charge density. Now, as your friend pointed out, the total charge is Q. But the total charge is nothing but the sum. I just divide all my space into very small volume elements, dV. Each one has a charge rho times dV, and I integrate it over all of my space. So that is my total charge, sum over the charges of all these dVs. And this would be, well, rho is A times Dirac delta r minus r. I have integral over r times r squared, integral over sine theta d theta, and d phi. Well, nothing depends on theta and phi. If you take those integrals, it just gives you 4 pi a. Well, the radial integral is easy to evaluate. I have that Dirac delta over there, and that Dirac delta tells me that I should just replace r by the radius of the sphere wherever I see it. So A is just Q over 4 pi r squared, and hence rho is equal to Q over 4 pi r squared Dirac delta r minus r. Well, Q is the total charge, which we know that it is distributed uniformly over the surface of the sphere. 4 pi r squared is the total surface of the sphere. So Q over 4 pi r squared is basically just charge per area. And that is what we call the surface charge density, which we usually denote by sigma.
Peki hocam Dirac delta'yı nasıl yapabileceğiz?
We will not. It stays there. But the integrals, I mean, the Dirac delta is this weird function, but it will disappear. I mean, when we take integrals, the integrals of Dirac delta will be well-behaved functions. So it just stays there. The charge density is a Dirac delta function.
Peki bunun türevi anlamında mı?
Of course, just like any other function, you can take its derivative. You can integrate its derivatives by integration by parts.
Bir de hocam şey soracağım. Mesela iki tane artı yük var elinde. Artı Q artı Q. Bu sistemin charge density'si ne diye sorsa.
Point charges.
Evet.
Let's say this is at R0, this is at R1. So if R is not equal to R0 and R is not equal to R1, what is the charge density? Are there any charges at points other than R0 and R1? No. This is 0. Now let's look at this. Let me just take this cube over here. The plus q charge is at the center of that cube with side length dh. Now rho at R0, we can just define it as the limit as delta q over delta v. As delta v, the volume goes to 0. What is the charge of the cube? Q. Whatever the size of the cube is, as long as the charge q is at the center, the total charge of the cube is q. The volume of the cube is dh cube. So what is this limit? As dh goes to 0, q is finite, so we have a number divided by 0. That is infinite. I can just repeat exactly the same thing for R1. So now again I have this weird function which vanishes almost everywhere, and it is infinite at 2 points. So the best candidate for such a function is A times Dirac delta R minus R0. Well, these are three-dimensional Dirac deltas. B times Dirac delta of R minus R1. So these two, both of the Dirac delta functions are 0 everywhere except then R equal to R0 or R is equal to R1. And this density just goes to infinity when R is equal to R0 or R is equal to R1, just like it should. Now we have to determine what these A and B's are. So let's just do the definition. So we have a plus Q. Let me call them Q1 and Q2. And we can just give them whatever name you want. Q1, let me just imagine this volume over here, V1. The total charge in that volume is Q1, but in terms of the charge density, I just divide it into small volumes. Each volume has the charge density times the volume. I sum over all of these, the charges of all of those small volumes, but I'm restricting my small volumes within V1. This is the total charge. This is equal to V1 A times Dirac delta cube R minus R0 dV plus B times Dirac delta cube R minus R1 dV. Both integrals are within V1. Well, I know that as long as I'm in V1, in this volume, R is never equal to R1. I'm within that volume, and R1 is not in that volume. Since R is never is equal to R1, this Dirac delta over here is always 0 within this volume. So its integral is also 0. Now, in the first integral, R is equal to R0 is within my volume. So this Dirac delta just tells me that to evaluate this integral in the integrand, whatever is appearing over here, wherever you see an R, just replace it with R0. That is how we integrate the Dirac delta. But there are no R's over there, so there is nothing to replace. It's just A. So that tells me that A is equal to Q1. You just repeat the same thing for V2. Let's just imagine another volume over here, V2. The total charge in that volume is Q2, but it is also the integral of rho of R times dV. But this integral, just repeat the same steps, is nothing but B. So now I know what A and B are. If I know A and B, those were the only things that I didn't know in my charge density. Now I know them. A is Q0, B is Q1. So this is my volume charge density for 2 point charges, one located at Q0, R0, with charge Q0, the other one located at R1 with charge Q1.
Başka bir şey söyleyeyim mi? Hani bir de hocam discontinuity yazıyoruz ya, işte bir alt eksi i eşittir sigma bölü epsilon zero. Oradan gelip bu rho'ya gidebilir mi? Sigma'dan.
Well, rho R is, if you only have a surface charge density, it is just sigma R Dirac delta, let's say n minus n0. You just choose a coordinate perpendicular to the surface, call it n. The surface is at the point n is equal to n0. We already did an example in your first question. You see here we have a surface charge density. Only a surface charge density. And the rho is nothing but sigma times this Dirac delta. The normal coordinate is the radial coordinate in this problem. So the R should be equal to the radius of the sphere. You can just generalize it to any other surface.
What it means to infinity?
Which one?
First we found that rho is close to infinity on the surface, then we found something different.
No, this goes to infinity on the surface. You see, when R is equal, the surface is when R is equal to the radius. That is how we define the surface. There we have this Dirac delta 0, which is infinite. Sigma is finite. The coefficient of the Dirac delta is finite.
So why we should show that rho goes to infinity?
It does. This also goes to infinity.
I mean, why we didn't the second part of the question directly?
Which second part?
Why starting from Q and find rho?
Now that is what we did. We started with the Q and found the rho.
But in the first part, we draw some boundary. Why we couldn't do directly from the definition?
Well, if you are confident with your definition of the Dirac delta, you could. What I was trying to do is, first of all, just show that the rho has the properties of the Dirac delta. So it has to be proportional to the Dirac delta. So that is what I was trying to show over here. And the properties of the Dirac delta are, it is 0 almost everywhere except in a single point. And at that point it diverges. So that is basically what we did over here. This charge density is 0 almost everywhere except in a single possible radial coordinate. And when the radial coordinate has that value, the charge density is infinite. So once we show these two properties, then we can be confident and say that the charge density has to be a Dirac delta function. In fact, just proving these two properties, that it goes to infinity on the boundary and that it is zero almost everywhere except on the boundary, we are actually proving that it is a Dirac delta function.
Displacement vardı ya hocam. Hani orada da böyle d out eksi d in yazmıştık. Onunla işte bu d out eksi in arasında bir bağlantı nasıl kurulur?
Well, let's say if you have a differential equation of this form, then V out minus V in over a surface is always equal to, let's say, sigma f in the normal direction. Well, or let's say this is G, this is G. G is kind of a density. And G goes to sigma G times Dirac delta n minus n0 on the surface.
Is electric potential vector?
No, I mean, this is, if you don't like the V, let's use B. This is any vector field. Now, if you have any vector field that has this property, that satisfies this equation, and G is such that it diverges on a boundary in this form. It is the G is a Dirac delta times some finite number on the boundary. Then this G appears over there. We know that the E field satisfies such a differential equation, the D field satisfies such an equation, and hence they all have such conditions on a surface. And the idea is, you see, if del dot B is equal to G, this tells me that you just integrate it over a volume. This is equal to B dot ds over any closed surface. This is equal to the integral of G over the volume bounded by that surface. And then to prove this relation over here, by the way, there is, let me rewrite it in a different form. This is not the correct form. This is the correct expression. So you take your surface, take some volume, evaluate B dot ds over the surface of that volume. That just becomes B out minus B in dot n ds in the limit that this height goes to 0. And this is at the same time equal to G dV in the limit as height goes to 0. Well, if G diverges on this surface, then that integral will be finite. And as you just shrink this volume, the volume goes to 0. Nevertheless, the integral will be finite because it has this divergence that looks like a Dirac delta. So this integral will be nothing but sigma corresponding to this G, whatever that G is, multiplied by ds. Just cancel the ds's, and you obtain this relation over here. Wherever you see a Gauss law, there is always this condition on the discontinuity perpendicular to a given surface.
In the previous question, the 2-point charge question, why for Q2 the rho goes to infinity?
For Q2? Well, let's just imagine this volume. This cube, let's call it dH prime. Rho at R1 is equal to limit as what is the total charge of that volume? Q2 divided by dH cube in the limit as dH goes to 0. Q2 is finite. dH cube goes to 0, so this is diverges.
Hocam bu elektrik alan için yazdığımız continuity'de net eşitliğin öbür tarafında ama burada bir tarafta kalıyor.
If curl of B is equal to 0, you combine these two. One tells you that, well, this tells me that the parallel component is continuous. So you have this vector field B on the surface. You can just decompose it into its parallel component and also the perpendicular component. Then if you look at the vectorial difference, if you look at the vectorial differences, the parallel components, they just cancel between B out and B in. What remains is only the component perpendicular to the surface, and that discontinuity is in the n direction, and it is proportional to the sigma g. I cannot obtain this result by just the Gauss law. I also need to know its curl. If the curl of this vector field is 0, whatever this vector field is, if the curl is 0, then I can move this n to the other side. But this first law is always true as long as you have this Gauss law. This is only true if the curl of that vector field is 0. For the electric field, the curl, we know that it is already 0, so for the electric field, we can write it in this form. For the displacement field, d of the displacement field need not be 0. So for the displacement field, we don't have this relation, but we can only write this one.
Peki hocam şu n-heti 1 diye bu tarafa atsam.
There is no division by a vector. You cannot divide by vectors.
Hocam bir ödevde vardı. Herhangi bir charge density belirtilmemişken sadece belli boundary'lerde potansiyeller belirtilmişken bir region'da potansiyel isteniyor. Bunda tek çaremiz zannedersem separation Ferrari'si kullanmak oluyor. Yani buradan genelleştirirsek bu gibi durumlarda işte şu yöntemi kullanabiliriz diyebileceğimiz bir
Well,
şey olur.
you see, in most cases, you will be able to apply more than one method to solve the problem. In most cases. Not in all of them, but in most cases. And so you have all these tricks now. We have the integration over the charge density, if we know the charge density. We have the method of images if we have, I don't know, an infinite plane conducting or between two dielectrics and the point charge. And then we have this separation of variables method if the boundary is reasonably simple. In a given problem, you should decide which method to use. But of course, for example, if there is a problem that you can solve using method of images, you can also solve it with the separation of variables. There is nothing that would prevent you. Well, what are the equations we have for a dielectric? We have the divergence of the displacement field, which was rho free. This was the equation we have. So the Gauss law is if you integrate D over any closed surface, this should be total enclosed free charge. This is your Gauss law. This will be always true, whatever closed surface you imagine, but it will not be always useful. It will always be true, but not necessarily useful. It will be useful if your system has sufficient symmetries, like the spherical symmetry or rotational symmetry, cylindrical symmetry. If it has such symmetries, then you can integrate the left-hand side in terms of the unknown displacement field. But in general, you cannot integrate the left-hand side if you don't know the displacement field. Well, if you know the displacement field, there's no point in, well, what are you looking? I mean, you are done if you know the displacement field. Exactly. No. It's, exactly. You see, the effects of the displacement of the charges in the system are in the displacement field already. You see, you remember displacement field, we had defined it as epsilon 0 times E plus the polarization. This polarization is created by these displacements. So that is why we call this thing displacement field. It is created, let's say, by the displaced charges. So the effects of all these displaced charges are already in the displacement field. What remains is the effect of the free charge, which is not in this displacement field. True. Exactly. So the rho free is 0 in that case. Well, you see, having rho free equal to 0 doesn't mean that there is no electric field. Your rho free can be at infinity. Or in your boundaries. So you see, this is the equation that D should satisfy inside your volume. You can put some inside your volume, rho free might be 0. You don't put any charges inside your volume, but you put some charges on the boundary. That charges on the boundary creates the electric field. For example, I think you had this problem, or did you? We had studied these problems of such a conductor, infinite. So this side was at the potential V0. This side was also at the potential V0. And then we said that the potential satisfied the Laplace's equation. Because in this region, inside these rectangular prism, there are no charges. The charges are on the surface. And the charges on the surface create my potential. Just like it happens over there. If you don't have any free charge on the inside your dielectric, you don't need to. Then the displacement is created by outside charges. the charges that are not inside your volume, which creates an external electric field which displaces the charges, and these displaced charges contribute back to the electric field, which changes the displacements and hence the electric contribution to the electric field, etc.
Hocam polarization sadece dipol moment için mi yazılıyor yoksa multipol için mi yazılıyor?
Well, if you want to, I mean, this polarization was due to the dipoles. In general, of course, from the quadrupole moments, you will get contribution, but they will be very negligible. Orders of magnitude smaller than this dipole moment. Okay, before we continue, just two announcements. One is about the recitation tomorrow. Before I came to the class, I checked there were only 3 students who were asking for recitation. So, I mean, I will also check tonight. So unless more students ask for a recitation, there won't be any recitation tomorrow. You can, of course, come to my office during that time. I will be in my office and ask your questions if we don't have recitation. The other announcements is about the homework. Okay, this homework is postponed for Friday, but about the future homeworks, there's a group of students who wants it Tuesday, a group who wants it for Friday. So now you can vote on the class. So whichever has more requests, we will just change the homework time one last time. I won't modify it anymore. But please, before I came, there were just 9 students who wrote their opinion. So the others also please write their opinion. When should you hand in your homework, either on Tuesdays or Fridays? My impression is that you would be better off if the homeworks are due always on Tuesdays. But just have your say. Other questions?
Hocam şu hani kapasitör elektrik dedik ya, orada şey yazdık, enerji yazdık. O kapasitörün içinde depolanan enerji değil mi?
True.
Elektrikle beraber içinde depolanan.
Well, you see, you have that capacitor, what we call the energy stored. Usually when we also define the energy stored in a given system as the amount of work that we have to do in order to construct our system, in order to bring the parts of our system all from infinity. That is how we had defined the energy stored before. But now the problem is, we already have a dielectric. Would we be interested in bringing the parts of the dielectric all from infinity also or not? What we will be mainly interested in, we have our system, which can be a capacitor already constructed. Somebody has already built the capacitor for us. But we will add additional charges to our capacitor and remove them. We will be interested in the amount of work that we have to do if we want to bring these free charges in our system or remove them from our system. That is what the energy that we wrote, 1/2 E dot d cubed r. This is the energy or the work that we have to do in order to bring the free charges to their final positions. For a linear dielectric, by the way. This relation doesn't hold if the dielectric is not linear. And for a capacitor, this just becomes 1/2 C V squared, where C is the capacitance in the absence of the dielectric multiplied by the dielectric constant. And this epsilon R is equal to epsilon over epsilon 0.
Şuradaki elektrik alan hocam toplam elektrik alan.
Yes.
Bunun içinde de gene D var.
Well, it is related. D is equal to epsilon E. The bound charges also contribute to this E and D. Well, the bound charges contribute to E.
Peki burada polarization ihmal mı ediyoruz?
No, the polarization is over here. The effects of the polarization are all parameterized in that epsilon, the permittivity.
I want to ask a question about displacement field and electric field for the capacitors who contain more than one electric boundary surface.
We already had solved this problem. We can also look at this one. Yes, your question?
What's the displacement field?
The displacement field. Well, let's look at the displacement field. In which one? Let's look at it.
Right,
The right one. So first of all, can we use the Gauss law? Well, what are the symmetries of the displacement field? You see, this is our displacement field. This is the equation that is satisfied by the displacement field, rho f. Now, the rho f is on our conductors. So here I have, let's say, sigma. Here I have sigma prime. Here, let's say I have minus sigma prime. The surface charge densities need not be the same. So there is no horizontal translational symmetry, which kind of complicates the problem. But I will make an assumption. I will assume that the displacement field and also the electric field, because the displacement field will be also perpendicular, proportional to the electric field, I will assume that both are vertical. There are no fringing fields. So the displacement field and the electric field, they are both perpendicular to the conductors. This is an assumption. It doesn't, I mean, there will be fringing fields which will violate this assumption, but for most of the system, this is a good enough description. Already we know that in the conductors, this electric field should be perpendicular to the conductors all the time. If we say that the separation between these two conductors will be very small, they will start perpendicular to this conductor. They should also end perpendicular to this conductor, so they don't really have space, distance to deviate from being perpendicular. So if it is narrow enough. So I will assume perpendicular. Now, if they are perpendicular, I can use the Gauss law. Because you see, the problem with using the Gauss law is that how do you evaluate the surface integral over a closed surface without knowing what the displacement field is? But in this case, since I'm assuming that the displacement field is perpendicular, I can take such a surface. Well, then this integral is just d dot ds on the side plus d dot ds at the top plus d dot ds at the bottom. Well, the ds vector on the side is horizontal. D field, I assume, is vertical, downward. So on the side, D vector and ds vector, they are perpendicular to each other. So this is 0. On the top, that is outside the conductors, there is no displacement field. So this D is 0 on the top. So this integral is 0. Now let's look at the bottom. I assume that D is perpendicular, vertical, pointing downward. The S vector at the bottom is also pointing downward. They have the same direction. So this is equal to D times ds on the bottom. But assuming that D lines are always vertically downward, or the electric field lines are always vertically downward, it basically tells me that the D doesn't change as you move. Well, it might change, but at every point on the bottom, since it's at the same distance from the conductors, the distance from the conductors do not change. At every point on the bottom, D is just a constant. So this is, since it's constant, I can take it out. What remains is the area. Let's call that area A. And the Gauss law tells me that this should be equal to Q free, which for that case, since I'm in the first dielectric, D1 times A will be equal to sigma times epsilon, epsilon 1 times A. No, sorry. Sigma times A, or D1 is equal to sigma 1, sigma. Well, I can do the same thing. I can just move this cylinder to the other dielectric. I will just do, everything will be the same except that sigma, now I have sigma prime. Well, I don't know what E, okay, so these are the D1s. I don't know, I know the E's. E1 is just D1 over epsilon 1, sigma over epsilon 1. E2 is D2 over epsilon 2. This is sigma prime over epsilon 2. I still don't know what sigma and sigma prime are. But what do I know is the parallel component of the electric field, parallel to any surface you can imagine, should be continuous. So if you have any surface, on one side there will be an electric field. If you take its parallel component, it should be equal to the parallel component of the electric field on the other side. Well, that principle I can apply to this surface over here. On one side of that surface, the electric field is E1. On the other side, it is E2, and both of them are parallel to my surface. So E1 should be equal to E2. So this gives me one relation between the sigmas. If I know the total charge, that would give me another relation between the sigmas, so I can determine what sigmas are. So what is actually happening over here, let's just consider the case of a single dielectric. So if you just put this dielectric between these two conductors, the medium will be polarized. This surface will be slightly negatively charged. The bottom surface will be slightly positively charged. But this positive charge will attract the negative charges. So there will be more negative charges in this region of the dielectric than on the other side. So that is basically what creates this inequality in the surface charges. The induced charges in the dielectric attracts more charge to the region where we have this dielectric. The charges over here will be larger. In the previous problem, basically the same thing happens. There will be both this dielectric and this dielectric will attract the charges into their region, but whichever one has a stronger attraction, it will correspond to a surface charge density which is larger than the other one. And the larger the dielectric constant is, the larger will be this attraction, because the larger the surface charge will be.
I did not understand why E1 is equal to E2.
Let's go back. Do you agree this one? If the curl of a vector field is equal to 0, then its parallel components to any surface should be continuous. Okay, so if you agree with this one, let us look at this case. What is the electric field at this point? E2, in which direction? Minus z, that is parallel to this surface, right? Just on the other side of that surface, the electric field is
E1 minus z.
still parallel to the surface. But the parallel component should be the same. It should change continuously. So if it is E1 on one side, it should be E1 on the other side. But we said that on the other side it is E2. So E1 should be equal to E2. Okay, let's give this 10-minute break, and after the break we can continue.